Welcome to the talk about Flatcar and Linux for Kubernetes and container workloads. So we're looking forward to a very interesting talk with regards to containerization and how to make containerization work in terms of OS usage in modern times. So I'm curious, teach us more about this.
Thank you. I just noticed that the headset is slipping too, so this will be a fun presentation. All right, so thanks for the introduction. So this is about a day 2 operating system that doesn't get in the way of your, let's say, business logic, basically not getting away in between you and the service that you're actually caring about. I'm Thilo. I'm a maintainer in the Flatcar Container Linux project, and now it's slipping off again. It's not really staying in place. I'll take it into my hand if that happens again. All right, so I'm on GitHub. I am very active on Mastodon, and if you want to reach out, you can just drop me an email as well. First, before we start, I have a kind of a little bit of an explanation of what I mean by day 2 in the talk abstract, but I don't expect you to read that. So what do I really mean? It's basically terms from operations, from DevOps, where you go, I don't know, if you start a project or even like a new company around a new service or product, day 0 basically is the point in time where you brainstorm a lot. You don't have a lot of code. You may have 1 or 2 of your most important features or business logic implemented. You don't really have regular users. You want to take care of exposing your service to, like, a very specific a very specific amount of users. It's the time of closed alphas. If you run a company with that, you're probably in stealth mode now. Your code looks horrible. It does the job, but it's basically write-only code, so you can't really read it or improve on it. It's proof of concept. Operations, it's hilarious thinking about operations in this stage. Operations are very manual. Things are very time-consuming. There's no time to actually, write actual automation because you wanna move with your business logic, with your application. And things constantly break, but that's fine because you're still figuring out things. Now, day 1 is a little more settled. You open up the service to general users. You emerge from stealth mode. You're trying to build your story out in the open. All of your main features are more or less implemented. You're still iterating. Code still looks bad. Your service actually meets reality with the first actual users onboarding and breaking things. And you're more or less constantly in firefighting mode. Your automation that you have, you didn't have time for automation beforehand. We just want to make your service work and iterate on your core business logic. Your automation is spotty, it's gappy. No one really has time to take care about that because you're still working on fleshing out your main features and making your actual code base more usable. There is testing in production, but not in a good way. And yes, there are a few companies and a few projects that don't really leave that stage ever. I hope you're not part of such a situation. It's not enjoyable. Now, day 2 is kind of, operator's heaven. Your project's mature, your code base is stable, it's reliable. You can put pressure and load on it and it doesn't break. All of your features of your application have a deterministic life cycle, like you know where to start, you know what to test, you have your test suites, your processes, and your releases defined. You don't really have user-visible service degradations or interruptions anymore. If something breaks, you're actually able to switch over to some spare that you run, so you can grow like an immense user base. That's the time of scaling. That's the time of not being paged in the middle of the night anymore because you have it all figured out by now. Your operations are well-defined. Your infrastructure is well-automated. If you have any service impacts, those are well-managed, like you have your runbooks and your playbooks in order, and you benefit from those. And so this is the stage where infrastructure maintenance is boring in a very good way. Like, you go to work, there are no surprises, it's awesome. There are projects that never reach the state, but as an infrastructure engineer, that's an awesome place to be in. So I'd like to talk about a operating system that integrates well with day 2. So it's not built for moving fast and breaking things. It's built for moving reliably and keeping things running without shooting your own foot. So this talk will have examples and some demos of Flatcar Container Linux, which builds processes and has some operational procedures thought into the operating system. I don't want to present features of the operating system. I want to present features of the surroundings of the operating system. It makes it easier for you to use it as a day 2 operating system. So I'll put a few assumptions here, and then we'll go through this list and we'll see if we can come close to actually reaching some of those requirements for a day 2 operating system. So in my world, in the operational world, my OS deployments are fully automated and reproducible, and that means if I install a new node in my cluster, or like a single size node, or whatever I'm using for my service, this is fully automated. I don't SSH into things. I don't need to fix things. I have kind of configuration lifecycle that helps me along. And the second thing I'd like to have is a reliable update or lifecycle management of the node. So when I deploy it, how do I update the operating system bits? How do I safely update them? And that kind of factors into the third point, like having a robust and safe way to automatically operate that in your target environment. Like, an OS doesn't exist in the empty space. It actually has to serve a purpose. And like, how well does it integrate in that purpose, or how well can you make it integratable? Configuration and inventory management is a thing that comes up if you run like a very large cluster. Because at some point, if you run thousands of nodes, some person or even some organization in your company will reach out to you and ask you, which version of XZ are you actually running? And then you try to figure that out. And it's an interesting place to be in if you've never thought about inventory management before. And the same is true for configuration management. Like, how do we start those containers? Like, how they're parameterized on the operating system level. And then you go in SSH, and then it's basically the thing that you don't do on day 2. That's a day 1 thing. Yeah, and lastly, how extensible is the thing, and how well does it scale into some tooling that you may need, or some other desires that you have. So the basic idea that we have in the day 2 operating systems, and Flatcar specifically, is if you operate a Kubernetes service or multiple Kubernetes services in a Kubernetes cluster, each of the pods of the service are basically throwaway. They're interchangeable, they're replaceable, they're commodities. And there's the overused phrase, cattle not pets. But can we take this approach and apply it to operating systems? And if we do that, how does the whole thing look? Right. So I promised you we're going to go through the things. We're going to start with fully automated deployments. So how do I install a node in an automated way so that it's reproducible, that your versions don't skew and run away through your cluster? Kubernetes services are deployed by having configuring sane defaults for the bits that you actually need to touch in the service. Sane values for the bits that you actually need to customize and to touch in your service. They come with sane defaults. You don't need to configure. You don't for instance, for MySQL pod in Kubernetes, you don't go out and you write the whole MySQL configuration. You have a few things exposed that you can customize if you need to, but if you just want to run a stock thing that runs on sane defaults, you can do that as well. And then you take your customization, like that makes it integrate in your environment that suits your needs specifically, you kubectl apply it, and your cluster automatically takes care of configuration management because it's in here. It takes care of version management, so you can basically update and change the version, roll forward, roll back, without ever interacting, in my example, with the MySQL binaries directly. And you have lifecycle management in your cluster built-in as well. Now, we have something slightly similar in Flatcar. There are some very obvious similarities in that the operating system is configured before provisioning. So you write your config before you even think about installing the node in a YAML format, as it happens, and we'll take a look at an example right away. And also, this uses sane defaults. So in the best of cases, if you only need a new node that uses your SSH key, you don't really have to write a lot, if anything, in that config file. If there's a storage device, it'll be used as the operating storage device, because otherwise, why would there be a storage device? And other things like that. So it uses sane defaults, and it gives you the opportunity to kind of tune stuff. But you don't have to if you don't need to. Now, you take this config and you feed it to the instance at provisioning time. And you can do that via custom data or user data if you're using a private or public cloud. There's always this field when you put in this data. You can provide it via HTTP. You can reach it. You can put it down on the instance via TFTP, IPXE. That works. And then when the node comes up, it self-configures at provisioning time, like only once when it's being deployed. And by default, it also has unattended updates activated. And that means it is self-updating. It's not just self-updating. We'll have a look at updates later on. It's also it's also able to roll back to a safe state if something with the update didn't work with your workload. But I mean, in very much the same way, you just provision your node how you would kubectl apply a service in Kubernetes. You don't SSH back into the node and do some fudging, neither manually nor automatically via tools like Ansible. We also don't use the cloud init approach of reapplying the config every time over and over again after reboot. This is rendered exactly once at provisioning time, and then it stays that way. And that has some benefits. I'm going to come to those in a second. So how does this look like? What's this configuration like? And here's an example. So this will work with minor adoptions for a number of day 2 operating systems. Like if you switch this and put Fedora CoreOS in there, it'll work on Fedora CoreOS as well. We're just creating a user here because I want to run my service as a user, not as the root user. We'll put an inline HTML page here. Then we render an inline logo into the configuration. And lastly, we have a systemd unit that just runs the caddy container, and that points caddy to the place where we put the HTML file. So I'm not trying to convince you to run single static HTML services in an individual virtual machine. This is more an example of how easy it is to set up a full machine with a caddy instance based on this. So this is the config file that we just looked at. And there's one more thing in here that I didn't have in the screenshot, and the one more thing is that I disable updates. And the reason why I disable updates is I want to demo updates in the next step. And it's bad if I use a self-updating operating system that would self-update right under my butt when demoing something else. So we're going to provision a node here. And as it is tradition, we will transpile the YAML into JSON. So transpile is no magic, it just runs butane, which is the config transpiler that we're using. And it will read the YAML, and it will also read the graphics file that was mentioned in the YAML, and it would just put it all into a JSON file. So if I now look at web.json, you'll see it's no magic either. It's basically what we've looked at before, but with the embedded website and the embedded graphics in the config file. And now I have a QEMU Flatcar image right here, and I have a command line starting it right here. So what we're doing is we're running the Flatcar QEMU image, we're passing the config file as a parameter. We'll route the host machine's port 8080 to port 80 in the virtual machine, so we're able to see the website. This is for SSH, which we're not going to use because it's fully automated. And also, I tell QEMU to just give me a serial console. Now, I said this page is very important, and it is. And you know, here's nothing. But now I'm going to run this. And then what it'll do is, at provisioning time right now, because it's the first time we provision that, it will render the caddy config, it'll dump the HTML file, it'll put the graphics file in place, and it'll take a few seconds for Docker to actually pull the caddy image. There it is. And what we're now gonna have is a web server running. So basically, given a static configuration, you create a web server that is repeatable. Like you can deploy this basically on any cloud provider or on your local machine or in your private cloud, and it'll always be that result. It'll always be this. So what you could do is you could take this, put it in a Git repo, and then have a versioned kind of way of provisioning your nodes. So this kind of provisioning is cloud agnostic, it's reproducible. If you take the same config file and you deploy it a year from now, it'll yield the exact same results. If you do it 1,000 times, it'll have 1,000 times exactly the same result. It is zero touch, so you don't really do anything with the node except watching it like we just did. There's no SSHing into the node, so there's no playing around in the node. You don't have any configuration drift. So you just check out the YAML file that I showed you. You provision it, and you can even automate that. And you will have the same configuration on the node. You can leave the node alone. It's self-updating. And half a year from now, it'll still have the same configuration. So if you deploy a new node, those two new nodes will be identical. It obviously supports more complex deployments than the static website that we just seen. One of the demos we have at the booth is we deploy a full-blown Jitsi server with streaming and recording capabilities, basically using the same approach. The configuration isn't much more complex for that. So if you want to have a look at that, come see us in the booth area, and we're going to run that for you. It also, so generating that YAML file integrates well into existing automation. We have Go bindings for generating that. We're actually using those with Cluster API. We have Terraform, OpenTofu modules that you can just use and automate basically generating that with slight amendments for the nodes that you're provisioning. And we're also fully integrated with Cluster API. So if you're using Cluster API, which is a management cluster to spawn Kubernetes worker clusters, then that will basically use the same approach. And it supports Flatcar. So I would check this off with fully automated, easy to deploy. We didn't even touch the command line once on the virtual machine. It's not your traditional way of installing an operating system from an ISO and then iterating on that until it looks the way that you want it to look, or even doing that and then producing your own operating system spin or image and then deploying from that, because all of that is too much work. You just parameterize what you want, and you provision it, and you have the parameterization under source control, and that's it. Which brings me to updates and lifecycle management. So now you've deployed it, and What about keeping it up to date? I briefly mentioned the XZ thing. We have regular issues with Docker that need to be fixed. So how do we do that and keep our services running? Now, taking a step back and looking at container applications in general, there's this neat thing of isolation that you have. I'm not talking about isolation from a security perspective, I'm talking about isolation from an operational perspective. So most obviously, to anyone who's using it, container applications have no interdependencies to other container apps, like they don't use libraries, shared libraries that other containers ship. They're pretty much self-sufficient, so you can just use them, and they bring everything they need to run the application contained in that container. They have no dependencies to operating system tools and services. You don't need specific command line tools installed in your operating system to run a specific container app, or at least you shouldn't, because, again, the image is self-sufficient. It only requires a container runtime and some kernel features in your operating system, and then you can run containers. So the configuration, again, that your container app uses is cleanly separated from the operating system container. Usually it would use a bind volume in some directory that you have under version control that you back up. And that's where the application would put its configuration, but your container application would never go to the operating system's etc and start parsing files. Or at least it shouldn't. It gives you portable applications. You just take a container image, deploy it anywhere, and it runs the same way anywhere. Now, if you look at this from the operating system point of view, then you see that there are huge benefits for container-focused operating to exploit with this kind of isolation. You have very well-defined interfaces between your operating system and the application, because you only need to ship very few components for your application to run. You don't have any other interdependencies, like you don't need specific versions of specific libraries. You don't need 3 different versions of Python in the operating system in order for the app to run. It's nicely abstracted and separated in the container. So, and by the way, operating system for us includes the runtime, right? So the operating system is the kernel and the user space that you need to run container apps. So if you look at it that way, then you see that the container runtime and the kernel features that make container apps run is the contract that you need to adhere to, that you need to uphold as an operating system to be interchangeable and to kind of entirely abstract from the container apps that you run. So from the operating system point of view, your entire operating system becomes interchangeable. If you just uphold the contract, if you focus on that contract. For many container-focused applications, this is used to provide atomic updates. In Flatcar, we're doing it in a way that we have a component in the operating system running that regularly checks for new image versions being available. And then it just stages new operating system versions right next to the currently active operating system version. And by upholding this contract, we can pull this neat little trick in where we reboot. We come up with the new operating system that still upholds the same contract. The application starts again, and it doesn't even notice any difference. But from the operating system layer, we've updated the core components that we need to maybe switch to a new kernel, maybe switch to a new systemd or to a new Docker, and everything's still running because we're focusing on that little green bar here. Which brings me to the update demo. Oh wait, that's the wrong. Here we go. So, I need to be root for that. So I need to stress that this is usually done automatically. Like no one logs in any Flatcar node and just types these commands. I do because I want to demo like what happens under the hood when an update is issued. I need my little helper here because okay. So. first I'll unmask update engine. I masked that in the ignition config that we looked at earlier. And I will unmask this so I can now start the service. And start it. Okay, update engine is started. I can now ask my update client on its status, and it just says it's twiddling thumbs, which is fine because it just starts. It's just started. So it checks for updates in regular intervals, and I can make it check right now by just telling it to check right now. And because I wanted to demo updates, I used the previous alpha version. I'm a dev, so I'm using alpha versions, and not the current alpha version. So this will actually find an update. So let's check the status again, and it's downloading. And you see the progress here, that's basically percentage, we're at 12%. And I'll just leave it downloading for a little while. Because, sometimes your very specific workload has issues with the new Docker version. You were using some old features that are not there anymore, and then now what do? The answer is simple. You just don't declare the new version as stable. You automatically reboot, and you fall back to a known state, known good state, because that's still there. It's still there, and all of that is automated. So you have your key apps that you absolutely need to have running, and they're not coming up after an update, after a reboot for an update. And then you just tell update engine, oh no, this is not working out, rollback. And then you just reboot again, and you're good. And your application is still running, so you have, you have time to actually check what went wrong. And that's my placeholder slide for the update demo, which is already downloading. I mentioned that R term here, and that R term is reboot. And some maintenance folks are scared of reboots. I'm not, but some are. So we need to, expose some advanced kind of customization in order for folks to actually, coordinate and customize the way they update. In the most basic case, a Flatcar node, as soon as it notices that the new update is there, we'll just download the update and reboot. At any given time, it detects the new update to be available. This might not be what you want. And the easiest part that you can do is you can define maintenance windows. So you can say every Monday at 1 a.m. in the morning, if you have an update staged, you can do your reboot. And then it does that, including the rollback if things didn't work. We have an update operator for larger clusters. So that's just the YAML you apply to your Kubernetes. It'll pick up a signal that we send on the node, and it'll coordinate reboots throughout your cluster. One of those operators is called QOD. It's a CNCF project. It's in larger clusters. I've seen it used a lot. But we also ship our own update orchestrator, which is called FluO, the Flatcar Linux update operator. And so both basically help you to coordinate those reboots in terms of, you might want to have at most that many nodes being rebooted during an update, and not like your whole cluster at once, right? It'll also help you with versioning and with rolling back. If you need even more control, what you could do, so the nodes by default use our open source update server, upstream update server, but you can also operate your own update server. This is a project that is part of the Flatcar project. And it allows you to basically control the spread of operating system versions throughout your cluster. Now, the update is through, and our status is now, I want a reboot. And if I wouldn't have disabled reboots in the configuration as well, then it would just have rebooted. But now it's just asking for a reboot. It also has created a file called reboot required, and that's actually something that QOD triggers on. So QOD just looks for this file, and if this file is there, it understands a node needs a reboot, so it coordinates the reboots in accordance with the parameters it was configured with. So before we do the reboot, let's check. We have kernel 6635, and we're running Flatcar version 4012.00. We're going to do the reboot now. Oops. And what will happen is grub will drop us into the new operating system, into the new partition, exactly once. After we've booted into the new updated partition, into the new updated operating system, it'll be declared as stable, as active after a while. And this is the window that you can use, or the dependency, the system, the service dependency chain that you can use to roll back. Like if you force a reboot within that window, or if you never have the new instance declared, the new version declared stable, then any reboot will bring it back into the old operating system version, and your app will be running again. So let's check. But we don't need that because our website is still serving. So the container survived. All right, I'm going to check that off for you. We have reliable update and lifecycle management built in. And this is something that you basically don't need to care about if you don't want to. It's very, very easy to automate. It's very, very easy to address issues if you run into issues with. And there are a few more advanced options, which I'll cover in a second. I promised robust and safe, but how is that being done even? Well, I've kind of hinted at it when I talked about the contract, right, between the operating system and the application. So this contract can, of course, be rigorously tested because it is just containers and running container applications. So it's really, really easy to write even complex scenario tests for that. And it's pretty straightforward to actually have this tested regularly. In our case, what we do, we have more than 100 scenario tests. So each green thingy here is actually from a GitHub Actions test run that we use. And so some of those are simple, like boot a new instance with the new version and check if like most basic things are there, if none of the system units failed and stuff like that. But there are also more complex tests here, like we test multiple Kubernetes versions, and that's like boot a number of virtual machines, install Kubernetes on it, put a CNI on it, and check if like all of the networking works. And that's only one of those. These tests, of course, run for every release, so we make sure that releases that go out are very solid and tested. For all of the channels that I'll be talking about in a second. But we've actually pushed this a little further, and this full test suite will be run for most of the PRs that go into the operating system. Flatcar is very minimal, so we can actually afford that, because building a whole operating system from scratch with all of the parts from scratch and running the tests is just a few hours. You can parallelize that for like every PR. Run it on multiple machines, and then you get that level of coverage. So putting this into place, we make sure that no PR actually breaks something in the operating system, no nightly and no release actually breaks something in the contract. And so we can make sure that even for major versions, major release versions in Flatcar, where major things can change, like a major kernel upgrade, major systemd upgrade, major Docker upgrade, still adhere to the contract because it's still able to run all of those scenario tests. You might not really trust me, and I would say we're 50% there, so I have a question mark there. And scenario tests are great, but they can never test your application, like the thing that you care most about. What if that uses kind of an edge case or some fringe condition or some old Docker feature that is not, sorry, it keeps slipping off, that is not present in a new version. So you want to guard against that, right? And the thing we will not do, like if you reach out to us and say, hey, this Docker feature vanished and now my application breaks, we will not send you back. We will listen to you. and we'll make sure that transition is as painless for you as it can be. So how can we actually have that level of support and help you with that? Now the channels, which I promised, come into play. So we have a number of release channels. Nodes are by default subscribed to the stable channel, which makes sense, I guess. There's LTS, which I'm not going to talk about much. And the other channels work like this. Sorry. There's the alpha channel. Alpha is fully tested. You've seen the scenario tests. All of those are run for all of the platforms that we support for every alpha. If something's red, we're not going to publish this alpha because we don't want to break things. However, alpha can contain half-done features. So it's not really good for production because you may find stuff in there that looks ready and you start using it and then it starts breaking because it's not fully implemented yet. So we use alpha for fast iterations for devs, and beta is actually as far as we go in saying this is production ready. Like you can use it. We can't do any more testing. And stable is what has been in beta for some time. Now, this is where you come in, right? Particularly if you run larger deployments, if you run a few canary nodes in your beta cluster, and you see new stuff coming in that we consider stable, but then, your canary nodes give you kind of a signal as this doesn't work in your circumstances. The thing you do is you report it back to the upstream project. And we have beta, our beta phases usually take a month or two. So you report it back and you say, hey, this is breaking my stuff here. We will never publish a beta that has known issues. So this is, if you run most of your clusters in stable, this is your surefire way to make sure your stable nodes will never see the things that you've detected in beta. And this is how we check the proven support for your target environment. Configuration and inventory management can be a nightmare with general purpose distros. For Flatcar, it's really a no-brainer. Because, as I said, we configure our nodes before we provision. It's rendered a single time at provisioning time. And then that's the configuration of the node. So what you do is you take your node configuration, you put it under source control, and then you have configuration management. There is no config drift, because nothing happens with the configuration of the node after it's been provisioned. So you're safe there. Software inventory management is another fun thing. I didn't tell you yet that Flatcar is entirely image-based. We are part of a small number of image-based operating systems that start to gain more and more traction out there. It's provisioned from a full disk image with a full set of tools in it. It is updated as a full image. What you've seen, just the update that you've just seen, it's just staging a new operating system image in a new partition. And it's immutable. We don't have a package manager. You can't add stuff at runtime. You can't write to /usr. If you're trying to touch operating system binaries, even with force by just writing to the underlying block device, it's DM Verity protected. So you'll have a signature failure and you won't be able to use the operating system again. We really, really want to make sure that the versions that we ship are the versions that are being used. So you don't have version drift. You look at your Flatcar version string and you know exactly which version of which package is in use in your cluster. So I mentioned earlier, when people go out and frantically try to figure out what version of XZ they're running in their, like every single node of their clusters. In this case, you just look at your node operating system version and you have it. It's pretty much top down. You don't need to do the bottom up research. So yeah, this is what you win with this, a priori configuration and with the image-based approach. Now, I'm trying to squeeze into the last, that's the wrong slide, sorry. I'm trying to squeeze into the last few minutes in how this can integrate into your specific environment. Because, as I mentioned, it's image-based, it's not meant to be adopted, or it's not meant to be taken to a spin, but sometimes you just need this one tool being present at the operating system layer because you just can't use it in a container. And the thing we've widely adopted for that is systemd sysext, up to the point where we ship core operating system components like Docker and Containerd as sysext integrated with the base operating system. You can disable them easily. We also use our own self-built sysexts published on GitHub to deploy Kubernetes, K3s, and things like this. So what is a sysext? A sysext is a file system image that contains only the bits of the feature you want to ship. Systemd sysext will merge it into your root file system at runtime, in our case, very early at boot. And so your root file system will look like it contains both the binaries of your plain root and of the sysext image. Sysext images are stackable, like you can merge as many sysext images as you want. You build sysext images by basically just telling make squashfs or mkoc to turn a specific subdirectory into a sysext, and then you're done. Why is it interesting for us instead of, say, traditional package management? Because it implements all of the foundations that we're using in Flatcar for extending the base operating system. There's a clean separation between operating system and the customizations, the sysexts. They even come with their own update story. So you can update your sysext. Say you want to use Kubernetes as a sysext on Flatcar because we don't ship Kubernetes. You can define your own update story for your Kubernetes sysext. And you can update it independently of the update cycle of the operating system, which is great if you want to switch to a new Kubernetes version and you don't really want to wait or synchronize with the release cycle of the operating system. It is very straightforward to build. As I said, you just use mksquashfs pointed to a subdirectory and it'll turn it into sysext, and then you're good. It's very easy to ship your own updates. You just need an HTTPS endpoint, and you set up systemd sysupdate to just pull this, and it'll just pull new versions as they become available. We're actually using it to an extent where we ship system-dependent sysext like ZFS or Podman or Python, none of which are included in the base OS because we want to stay lean. But all of those have a dependency on the base OS, the C library, the kernel, and whatnot. We just ship these selectable with the operating systems. You can just activate them by writing one single line in a config file, and then you'll get them at first provisioning, and they will update with the operating system because they need OS libraries. But more interesting for Flatcar users is the system-independent sysext, basically statically compiled stuff like Docker, Kubernetes, WASM runtimes, and those can be managed entirely differently from basically our part of the bargain, of the contract. And you could basically use them to extend the operating system yourself. And I hope we have enough time for the So all of this sounds like insanely complicated. How would you start using those weird file system images, the sysext, and how hard is it to actually bring them into, for instance, Flatcar? Now, let's check the YAML configuration of just a Kubernetes deployment that I want for my Flatcar node. Now, you see again that I switch off reboots, so I'm not gonna talk about that part. So this is what you need. This is 4 lines of configuration. You would consume, in this example, the Kubernetes sysext from our sysext bakery, which is part of the Flatcar org, on GitHub, and which we update regularly. And then you would basically create a soft link here to make systemd aware of that there's a sysext it's supposed to use. So let's transpile this. Put the JSON file into my image subdirectory here. and then start this again. So in this case, I'm not going to expose any ports. And this is probably a point in time where I should point out that I'm using QEMU in snapshot mode. So every single time I entirely shut down the virtual machine, it'll just forget all of the changes that it would usually have written on disk, which is very handy if you want to demo stuff for an operating system that is only configured one time, and that is at first provisioning. So what we're going to see now is that ignition during boot will just pull the Kubernetes sysx. There are other ways you could use that. The sysx bakery actually gives you a tool called bake Flatcar image, in which you could bake the Kubernetes sysx right into the image before you provision it. If you want to optimize that way, that's definitely something we support. And now I can run kubectl, which I didn't do before, so you don't really know that it's not on the base OS, but I can systemd sysx list this for you. And so you see what we had in the config file, this soft link here, which is in reality a soft link that goes into opt. This soft link here was created by our configuration, and if I remove this and then do a systemd sysx refresh, you'll see that, oh wait, I did this as the user. You see that kubectl suddenly doesn't even exist anymore. And that's because it's not merged in the root file system anymore, it's gone. Kind of showing that the deployment that we did actually made it appear. So, and in this way, if you need to have your own custom tooling for your operating system on top, this is how you can integrate with your processes in a very flexible manner. And for your own tooling layer, you can even define your own update cadence. You don't need to rely on the operating system. And that's pretty much it. I hope I'm still in time. Cool. We're a pretty open community. This is a purely community-driven project. There are no companies behind it making money from it. We're very active at Metrics and Slack. We have office hours calls. If you want to join as users or as developers, we run office hours calls every second Tuesday. We have a DevSync call, which is slightly more developer-centered, every fourth Tuesday. Those are just Jitsi calls. You can run it in your browser and participate. They're live streamed to YouTube if you just want to watch. All of our planning, long-term planning, roadmap, short-term implementation and release planning are on GitHub. These are GitHub project boards, so you basically see everything that we're doing. There's one, this slide is slightly outdated. We've submitted Flatcar to the Cloud Native Foundation as incubating project, which is the first Linux distro ever submitted to the CNCF. We were accepted 2 weeks ago. We're now a CNCF project. Thanks, folks. That's awesome. Yeah, that was it. Any questions?
So, if there are any questions, please put your hands up.
Thanks for the presentation. My question is something is the difference between CoreOS.
Yeah.
It looks like CoreOS for me.
Yeah.
And this one, why I should use this?
Depends on what CoreOS you're talking about. There was the original CoreOS, which was kind of discontinued when Red Hat took over CoreOS. And if you want to use that, then you want to use Flatcar, because we're a friendly fork of that original CoreOS. We're using all of their bits and pieces, but we obviously modernized a lot in that distro. If you're more interested in Fedora CoreOS, good reason for using that is Red Hat builds their own Kubernetes solution, OpenShift, on top of that. So Fedora CoreOS is reused in Red Hat CoreOS later on. So if you're more an OpenShift person and you need like all of that full-fledged Red Hat support, that's a good reason to use Fedora CoreOS. There's also SUSE microOS, which is very recent. I want to mention at this point. And the reason for that is, I think it's very important we line out that we're not alone in the world. We're collaborating with SUSE microOS and Fedora CoreOS on the very init system, like this ignition stuff that you've been looking at. We're all using it. We're all contributing to it. And I think that's very important to say. But if you like the original CoreOS, or if you liked what I've demonstrated you today, or if you want unmatched support of cloud providers, we provide a few more vendors than Fedora CoreOS because they have this focus on Red Hat OpenShift and like the platforms they run on, and they support that very solidly. But we're trying to more go, into the breadth and supporting more platforms like that. People working for cloud providers actually started contributing to Flatcar. We have contributions from Hetzner, from Akamai, just because they're interested in getting it to run on their platform. All of the three that I mentioned are very, very good image-based container operating systems. So it really depends on the use case.
Are there any further questions?
Thank you for the talk. Two questions. One is, why are you basing this on Docker instead of Podman? And the second is, would you recommend, or would Flatcar be able to run non-containerized workloads? Because you said SysEx is basically a way of installing more software, and I just use it as a head virtual machine OS, basically, as like a Google container, or?
Depends. So let's start from the beginning. Why Docker and not Podman? Actually, it's mostly legacy. So Docker is very widespreadly used. So that was the first thing CoreOS was supporting. So we keep continuing that support. However, I think since a few months, we're now supporting Podman as well, optionally. That's an optional SUSE you can activate. It's fully tested. It's fully supported by upstream. You can even mask the Docker SUSE, so you wouldn't see Containerd and Docker anymore. The thing with Podman is, Podman's based on crun, and crun is system dependent. So you would need to update Docker and lockstep of the operating system. Something that, you need to update, Podman and lockstep of the operating system, something that Docker doesn't need. So we ship it, we provide it. It needs to be a system-dependent SysEx. But yes, you can absolutely use Podman. Regarding any other workloads, it's really about the contract, right? So if you want us to stay true to this contract and to make sure that your workloads actually continue to work across updates, across versions, then we can best guarantee this in having like a well-defined contract, a well-defined API here. And this is what containerization and containerized apps give us. You would lose that with SysEx, and you would potentially, because SysEx are not isolated, they're just files in your operating system, you would potentially conflict with the operating system. But if you can ship a SysEx that is isolated, by using, for instance, Go services or by using static compilations, you could actually use SysEx in the same way that you would currently be able to use containers.
Are there any further questions? If there aren't, then thank you very much. And